Hello students. In this video we are going to apply the mean value theorem for definite integrals on the Taylor series remainder term so that we can get the expression without the integral term that you often see with Taylor series. So if you haven't watched my video on the proof of the mean value theorem for definite integrals, I recommend that you watch that video, or at the very least watch the first minute of it so that you can get the statement of the mean value theorem for definite integrals, or just look it up in your calculus text or something online. But you're going to need to be aware of what the mean value theorem for definite integrals is in order to follow this discussion. So I'm assuming that you've done that. Now we have that t is between x naught and x. Okay. We could switch the direction of x naught and x, and I'll address that later in the video. It's really just a without loss of generality case. If you switch those directions, you really don't change this result. The result would be exactly the same. All right, so let's just proceed just with this assumption here. All right, so if x naught is less than t, which is less than x, right? T's on that interval, then I want to apply the mean value theorem for integrals. So what I really need to do is I need to try to convince you that this term here, this x minus t to the n, does not change sign on this interval. We're already assuming that this derivative is continuous. That has to be by assumption to perform the Taylor series expansion. But it's this term that we need to not change sign. So if I multiply everything by a -1, then I switch the direction of the inequalities, and then I add x to everything. So x minus x is 0, x minus t, and x minus x naught. So if x minus t is greater than or equal to 0, then of course x minus t raised to the nth power would be greater than 0. And likewise, look, if the inequality went the other direction, then you multiply everything by -1, you switch to inequalities. You add x to every side, to all three terms in the inequality, and then you get that x minus t to the nth power is always less than 0, so it does not change sign. So as I said before, you can just go with, let's say, this assumption. All right, let's proceed. So this term here, as I promised, does not change sign on this interval, or likewise if you needed to switch direction, it doesn't change that interval. And by assumption, this term here is continuous. Otherwise, we wouldn't be doing the Taylor series expansion. So that means that the integral mean value theorem, which I'm assuming you've looked up or watched a video and seen the proof, that integral mean value theorem for definite integrals applies. So let's use it. All right, so now we have that this term is does not change sign. This term is continuous, so that means there exists a c in this interval from x naught to x, so that we get this expression. So we put the c in for there. And so that c is some theoretical value on this interval. We don't know what it is. We just know that it exists. Okay? So I'm saying this statement gives me this equality here. That's the integral mean value theorem, or the mean value theorem for definite integrals. All right, I'm going to clean this up. And so I just rewrote this term here, but I factored out the n factorial. Okay? Now I'm going to integrate this term here. Now to integrate this, remember, we're integrating with respect to t, so there's a minus sign in there. Okay? So there's a -1 that's going to pop out of the integral when I perform the integration. And you could either just see that, or you can, if you need to, you can just do a U-Substitution and let u equal x minus t, then du equals minus dt. And then when you plug in, remember t is x naught, so if you plug in x naught here, you're going to get an x minus x naught in the bottom limit of integration. And if you plug in x here, you're going to get x minus x is 0, so you're going to get u equals 0 in the top limit of integration. This minus sign came from the U-Substitution, du equals minus dt, and now we have u to the n. And so if I swap the order of integration and I go from 0 to x minus x naught, then I change the sign of the integral, and now I have a positive integral, so that minus sign will go away. And I'm integrating now u, and I've changed my limits of integration from 0 to x minus x naught by doing the U-Substitution. And so when we integrate that u to the n, we get the n plus 1 for the exponent, and we're dividing by n plus 1. But keep in mind that n plus 1 times n factorial, that's the same thing as multiplying by the next term in the factorial. So this is going to collapse to n plus 1 factorial. And when I plug in 0, I will get 0. And when I plug in x minus x naught, I'll have x minus x naught to the n plus 1. And you're going to see that we will not get the result of the remainder term for the Taylor series. Okay, again, this is just an, so imagine if you had 4 factorial and you had a 5 here. Then 4 factorial times 5 gives you 5 factorial, for example. So n factorial times n plus 1 gives you n plus 1 factorial. This is the term, the derivative term that we get from the integral mean value theorem. And I just integrated this polynomial here, and we get x minus x naught to the n plus 1. And this is the remainder term for the Taylor series. All right, good luck.